Okay, so we're continuing to work on limits, and we've looked at limits graphically and seeing if it exists or not and showing if it did or not. We've looked at limits algebraically, where we go in and we just basically plug in those values wherever we see the variable that we're going to. And now we just looked at the end of yesterday, limits going to infinity or negative infinity. And so we're going to go through some more examples. We also looked at forms when you're doing it algebraically, maybe getting in a form of an indeterminate form where you get 0 over 0. So we're just going to go over some more problems of this, and maybe look at some of these piecewise functions down in here and these examples that I had pulled. Okay. We also saw at the end of class that if you had the limit as x goes to infinity, or negative infinity, I'm just going to put infinity in this case, 1 over x, or x to the n, this is equal to 0. You have 1 over a huge number that keeps growing, it's going to be going closer and closer to 0. And we can use this fact when we're taking limits. So for instance, if I wanted to look at, and I might have pulled some of these problems, and I'm sorry if I had. Let's look at this limit as x is approaching infinity of 2x squared minus 7x to the 4th all over 9x squared plus 5x minus 6. So if we go in here and we plug in infinity wherever we see an x, basically you're getting something like infinity over infinity, which is another indeterminate form, which means it doesn't tell us anything, and we need to go back and we need to look at this limit. So if you get anything in the form of infinity over infinity or 0 over 0, we need to relook at it. So this again is an indeterminate form. So this doesn't tell us anything. So this doesn't tell us what's happening on that graph. So a way to deal with it when you're getting infinity over infinity, and we have powers like this, a polynomial in the numerator, polynomial in the denominator, then what you want to do is look at the degree of the numerator and the degree of the denominator. So the term with the highest power, this would be this negative 7x to the 4th. But really it's this. I'm sorry, I shouldn't have done that. X to the 4th. So I'm really just kind of looking at this variable to this highest power, and then we're looking in the denominator. And so looking at the highest, the variable to the highest power there, we have that x squared. And so determine which one's larger. Well, x to the 4th is larger. And so what we're going to do is we're basically multiplying this by a fancy 1 to manipulate it to give us information about this limit. And that fancy 1 that we're going to multiply by is 1 over x to the 4th in the numerator and 1 over x to the 4th in the denominator. Okay, let's just do it here. So basically we're multiplying this by 1 over x to the 4th minus 7x to the 4th all times 1x to the 4th. And then we have this 9x squared. We also multiply that by 1 over x to the 4th. So it's like I multiplied this to the numerator denominator. I'm just distributing it right now to each term. Okay, so we have plus 5x times 1x to the 4th and minus 6 times 1x to the 4th. So we're going to use our rules of exponents. And so if you're looking at this, we have 2x squared over x to the fourth. So we can reduce this, and that would leave us with an x squared in the denominator and a 2 in the numerator. So simplifying this, we have to carry this limit down until we actually use it and plug in that infinity wherever we see an x. Okay, so again, 2x squared over x to the fourth reduces to 2 over x squared minus, well, 7x to the fourth all over x to the fourth, those x to the fourth cancel, and we're just left with a 7 all over, so 9x squared times 1 over x to the fourth. That gives us 9 over x squared plus 5x times 1 over x to the fourth. That reduces to 5 over x cubed minus 6 over x to the fourth. Okay, so now when we go in there and we plug in this infinity wherever we see an x, we would have 2 all over infinity squared. It's kind of bizarre. Minus 7 all over 9. And that 9 is over infinity squared plus 5 all over infinity cubed minus 6 all over infinity to the fourth. Okay, those are powers to those infinities. Well, something over something that, a number over something that is huge or going to infinity, again, goes to 0. And so we have this piece right here in the numerator, 2 over infinity squared. That piece of that expression goes to 0. And then we have minus 7 all over, well, 9 over infinity squared goes to 0. 5 over infinity cubed goes to 0. And negative 6 over infinity to the fourth also goes to 0. So if we look at this, we're left in our numerator with the negative 7 all over pretty much 0. And so if you have a number other than 0 divided by 0, it's undefined. So what this is telling me is if I was to graph that function, the end behavior of the graph, it's either shooting up to positive infinity or negative infinity. And to this case, it looks like to me it's going to be going to negative infinity. But let's pull it and let's look at the graph of this. So we're going to go to desmos.com. I'm going to use their graphing calculator. Okay, so my numerator, I believe was, no, I don't even remember. Something minus 7. 2x squared minus 7x to the fourth. Just write it down. All over 9x squared plus 5x minus 6. So 2x squared minus 7x to the fourth all divided by 9x squared plus 5x minus 6. Kind of funky graph. that this graph actually is something that we were going to look at today. If we get into continuity, notice there's jumps in this graph here. So notice there's actually what is called a vertical asymptote here. And so as x is getting closer and closer here to -1, on the left, it's shooting down to -infinity. And as we get closer and closer to -1 on the right, your graph shoots up to +infinity. And it looks like, again, you have another asymptote, like around 1/2 or maybe a little more. But notice here, this is our end behavior of the graph. So as x is going to +infinity, notice that this graph is going downwards forever, and it's going not to one particular value, it's going to -infinity, which we determined before. Okay. If you had taken a class that you know how to graph rational functions, then you should know that looking at the degree of the numerator or denominator, you can tell if you have a horizontal asymptote or not. Horizontal asymptotes, those are the values where your graph is hugging that y equals line as it goes to infinity or -infinity. If they're the same degree, then it's going to have a horizontal asymptote. But if the degree of the numerator is larger, it's always either going to go to +infinity or -infinity as x goes to infinity. So let's look at piecewise functions. So piecewise functions, those are functions where there's multiple equations that you use, and it depends on what your variable is, depends on what equation you're using. So for instance, just pull this. Let me just pull this down here. So let's look at just the first one. So let's say we were looking at this piece right in here. So we're looking at the limit as x approaches -1 of f of x. And we're given that, again, f of x is equal to, it's going to be equal to the equation x cubed plus 2 if x is not equal to -1. And it's equal to 5 if x equals -1. Okay, and we want to look at the limit as x is approaching -1. So notice that our equation is changing at x equals -1. And so we need to worry about what's going on there. And sometimes it's helpful to graph it. So basically, it tells me x is equal to 5 when x is -1. So I'm going to just graph that point. So basically, that is just saying a point here. So this is saying we have a point at, and when x is -1, y has to be 5. So I'm going to have a solid circle there. And then any other value you plug in for x and choose, you have to plug it into the first equation. And so we can just kind of plug in points there. So if we plugged in 0 here for x, right? 0, this would give us 0 plus 2, which is 2. So if we plugged in 1 for x, so we have 1 squared is 1, 1 plus 2 is 3. Also notice that that is a quadratic. 1 and 3. So I know it's a parabola shape. I also know if you're thinking about this, actually that's a cube. So it's not necessarily. That's not a parabola shape.
Should that be x cubed?
Yeah, that's a cube. So I still get the same thing, fortunately, for those other ones. So 1 cubed is still 1 plus 2 is 3. And 0 cubed is still 0 plus 2. So thank you. I was just noticing that. So if we plug in 2 in there, we get 2 cubed is 8, and 8 plus the 2 gives us 10. So that's going to be way up here. Okay. So I just know it's kind of going up like this forever on this side. I actually need to see what's going on at -1, even though that is not a piece of the graph. So we want to plot an open circle. Oops. When x equals -1. So if we plugged in -1 there, we would get -1 cubed plus 2. And -1 cubed is -1. And so that would give us -1 plus 2, which is 1. Okay, so we have an open circle at -1, 1. And then if we plot 2 in there, so if we put, I'm not negative, so -1, 1, open circle. And then let's look at numbers less than -1. So let's say -2. If we plug in -2 and cube it, you get -8 plus the 2 here. So -8 plus 2 is -6. So we have a point at -2, -6. So that's what the graph of that piecewise function is. And now it wants us to look at the limit as x is approaching -1. And so when we're looking at the limit as x is approaching -1, we want to look at what's happening on the left-hand side. So we denote it with that little negative in there of f of x. And so as we're coming in on our graph, getting closer and closer to this -1, we want to see what's happening to the y value. Even though it doesn't equal that y value of 1, it's getting closer and closer to the y value of 1 on the left. And then same idea when we're coming in on the right-hand side of this graph to -1. Again, you're getting 1. So the limit as x approaches -1 on the right of f of x is also equal to 1. So again, in order for a limit to exist, they both have to be identical, and we get the same y value coming in on the left and the right. And so we say the limit as x approaches -1 of f of x is 1. So this is actually kind of what I was going to talk to you about today with continuity. And so let me just kind of explain here because it kind of ties it in really well, and we'll go back when we get to that section and talk more about it and do more problems. But in order for something to be continuous, the limit has to exist, which it does, right? We just showed that the limit exists. Left-hand side has to equal right-hand side, and it has to be defined at that value. Well, it is defined, right? When x is -1, we do have it defined. We do get a point of, I believe it was 5. But it also has to equal f of -1. So to be continuous, let me just write that down. So to be continuous, x equals -1, the limit has to exist. It has to be defined. At x equals -1. And the other stipulation that has to hold is that limit as x approaches -1 of f of x has to equal f of -1. So if all three of these hold, then it's continuous. So when you were going to be proving something's continuous at a value, we're going to show that all three of those things hold. And if we're proving that something or showing something is not continuous at a x value, we can show that at least one of these. Once we get one of these doesn't hold, then we can just say it's not continuous there. Notice that f of -1 we had seen was 5. So up here we said f of -1 was 5. And so notice that this does not equal f of -1. So condition 3, and what I called 3 in this case, doesn't hold. So this condition doesn't hold here. So it's not continuous at -1. If there was no point there at all, like the one above it, and that was just that open circle here, if this piecewise function would have just said, okay, well, in this case, it doesn't really matter. It would be weird if they had a piecewise function if we did this. But if they said, if x is -1, we chose your point to be 1, notice that would have filled in this circle here. And that is called what is called a removable. We can define a point to go in that open circle, and then that's a removable discontinuity. That's not always possible, but sometimes it is. And that's, again, something else we'll talk about maybe today or next week. Let me see. Maybe let's look at another one. So how are you guys? Do you remember graphing piecewise functions before? Just kind of seeing where you guys are at with that. Okay, so on the participation, so go down to participant. If you don't have that little thing pulled up, pull it up, and you have yes or no. Would you be able to graph a piecewise function? Put yes, if not, put no, which is okay. Just trying to feel where you guys are at. Okay. Oops. That didn't work. A little more, half of you have voted. This should be easy participation. Yes or no, you understand how to graph a piecewise function. You think you could do it, or no, you can't, and we need to go over it more. So 15 out of 24 voted. We have 9 more people to go, 8 more to go. Some of you guys fell asleep. You're still in bed. You can watch the lecture from bed. Oh my goodness. I'm putting you guys to sleep. Okay, let's so it's kind of like a half-half. Half of you think you can do it, half of you don't. So while we're doing this, if you think you can do it, maybe you should be trying this on your own, and I'm going to be kind of talking through it as we go. Let's do this one that has 3 equations. Let's just first talking about the graph, and then we'll get into the limit piece. Okay, so we have f of x. I don't like that this. I want it huge. Okay, f of x. I like my pins really thick, but it seems like it's not doing it anymore. Oh well. This is equal to the piecewise function. So we're going to use just the piece of the graph, x minus 1, if x is less than 3. We're going to just graph the line 2. You know what? It's going to be difficult right now because, well, the program is being difficult. I'm just going to exit out of it and come back in because I want colors when I'm graphing this. Sorry. So we can graph each piece in different colors. Okay, once again. So we're looking at, again, this f of x. This is equal to x minus 1 if x is less than 3. We're going to have just 2 if x is between and including 3 and 5. So 3 is less than or equal to x is less than or equal to 5. And we're going to use the equation x plus 3 if we have a value of x which is bigger than 5. So when you're graphing piecewise functions, you're only plugging in the value of x where this is defined. And so when we're choosing values to plug in for x, any number that we choose is less than less than 3, we're using this equation. The thing is that we want to see what's actually happening on the end values of these inequalities, because this is where our graph could be making some jumps. And this is where our graph is getting really, really close to on the left or right, depending on which inequality you're looking at, or maybe even both sides. And so if it is an inequality that is strictly less than or strictly greater than, we're going to look at that, what it's happening at this value, and we're going to put an open circle. So we got 3 separate equations. And I'm always going to look at what's happening on the interval. So let's just start with 3. And so if I went in and I plugged in 3 into this equation, I get y equals 3 minus 1, which is 2. But I usually kind of make a note to myself to remind myself this is an open circle here. Now I want to choose numbers that I could use in this x minus 1, so it has to be numbers less than 3. I know this is a linear line, so you guys could use some of the information by graphing it that way. I know my y-intercept is -1 and my slope is 1, or you can just plot points. And so a number less than 3 would be 2, 2 minus 1 is 1. I have a point at 2, 1. If I plug in 0, 0 minus 1 is -1. So usually knowing the shape of that piece of the graph is helpful. Okay, so graphing this, I'm just going to graph what I have in the blue for a second. And so I'm going to have problems. I should make it over here more. Okay. Okay, so again, we have a point at, or open circle at 3, 2. So I'm going to do my open circle there. We have a point at 2, 1. We have a point at 0, -1. And so my graph is going to be coming down on the left of that open circle. I'm not extending this piece of the graph to the right of this open circle. So we need to stop. So now if we go to the piece that says, okay, f of x is equal to 2, and those are for values between 3 and 5. Well, if I have basically x, and this is the same thing as saying y equals 2, I know y equals 2 is a horizontal line at 2. And we want to see what's happening at our n values of our inequality. So I have an n value of 3 on this inequality. And if I plug in 3 into this equation, well, there's no x there. My y value is still 2. I'm going to put, again, a note to myself. This is a closed circle because of this equal sign on the inequality. And so we're going to graph the point 3, 2. So notice that actually was the same as my open circle of 3, 2 from the other piece. So I'm going to now get to make this solid because of this value. And at 5, well, again, there's no x here. My y value still remains 2 at 5. It's a horizontal line. And this is also a closed circle because it's less than or equal to. So for this green piece, I can't extend that green piece to the left of 3, and I cannot extend that green horizontal line to the right of 5. I have to stop there because that's the values of my x for this piece. And then the last piece is x plus 3 for x greater than 5. So look at the n value of our inequality, which is 5. So we want to see what's happening there, even though in this case it's not defined. And so we plug in 5 for x, we get 5 plus 3, that's 8. And this is an open circle. And so let's plot 5, 8. So if I go over to left 5 and up 8, I have an open circle here. And then it's any value that is bigger than 5. And so if I plugged in 8 in here, I'd have 8 plus 3, which is 11. So, and that's solid. It's going on forever in that direction. It's a line. And so we have, and we can't go to the left of this x equals 5 for this black piece of this line. So in this piece, basically I'm using just the values bigger. Second one, I'm using in between and including 3 and 5. And the other piece, I'm using the x values, which are, oops, to the left of 3. Okay, so any questions about that graphing the piecewise function? Oops. Okay, let me clear your results. So going back to that participation, do you think you could now, kind of thinking about it and stepping through, you're just graphing each section of the graph, could you graph a piecewise function if you were asked to? So that's probably definitely going to be on your a test. Thumbs up works too. And you don't need to be embarrassed if it's been a while and you don't know how to do it. Again, I'm okay with you saying no. I'd rather you say no than being embarrassed and not answering at all. You guys aren't going to judge, right? If somebody doesn't understand something, you wouldn't judge. It all takes us,
No way. I'm the first person that doesn't usually understand.
we're all here to learn. Okay. Hopefully you're here to learn. Okay, let's go down to the problem. Now let's actually go and look at what they're asking us. It did want us to find a limit. Where did it go? And the limit we wanted to find was as we were approaching 5. Oops, first one. We want to look at 2 pieces. And these are the 2 pieces where we would have jumps possibly in the graph. So we want to look at the limit as x approaches 3 and x approaches 5. And again, notice that those are the values that are the in values of our inequality. And so those are the values where we would have problems if we had it. And so I can technically see as x is approaching 3 that we're getting that y value of 2. So here's our 3. And if we go up here, notice that it ended up being a closed circle. And if we come in on the left, we're getting 2. So this would actually equal 2. And technically where you're plugging that in, because we're coming in on the left, notice that this is a number, because it's on the left, is smaller than 3. And so when you're plugging it into this equation, make sure that you're plugging in to the top one. So coming in on the left, we would be using this x minus 1. So plugging in 3 there, we show that this is equal to 2. If I'm looking at the piece though, where I'm coming in on the right, well, this is a number that is bigger than 3. There's a couple of equations that are that you use when you're bigger than 3, but you're going to use the one that is directly to the right of that f of x value. And so when we use this equation and plugging it in, you're just plugging it into this 2. Well, I don't see an x here, so that's just result is 2. And so then because the left and the right are the same, we can say that the limit exists. And the limit as x approaches 3 of f of x equals 2. But I also wanted the limit as x, other piece was the limit as x approaches 5. And so this is where we have 5 on the graph. And I go up to the left. And I get that this is a y value of 2. So if I look at the limit as x approaches 5 on the left of f of x, this is equal to, so the equation on the left of 5 would be this middle piece 2, and that's equal to 2. This time we're going this way. And then if we're looking on the right though, so we're using directly to the right of this piece is this piece. And so if we're coming in on the right-hand side, we're getting closer and closer to this y value of 8. And so this is equal to 8. And since these are not the same, they're not equal to each other, the limit as x approaches 5 does not exist, or f of x does not exist. Okay, so let's look at one more. We actually probably could have done this without graphing, and some of you probably are saying, yay. Why didn't you just tell us that in the begin with? What we could do is basically, like I was saying, you know, when we're looking at an x value that we're approaching, and it's one of the pieces on our inequality, we're going to have to see is the left and the right the same. And so let's look at the other piece. Oops. Just helps me to pull it down so I don't have to go back up and refer to it. Okay, so I'm looking at this last one. Let's look at this. So we're given that g of x, so g of x is our function. And there's 3 separate equations for g of x. The first equation is just 5. And this is if x is less than 0. The second equation we get is x squared minus 2. And this is if we have values of x between and including, so 0 is less than or x, which is less than or equal to 3. And then, oops, sorry, yeah, no, I thought I had was reading the wrong one. And then the last equation is 7. And this is if x is greater than 3. We want to look at the values of our limits where it's changing values. So notice that it's changing graphs at x equals 0, and it's changing graphs at x equals 3. Or not graphs, well, it is changing graphs and it's changing equations because of that. So, oops, I wasn't going to graph. Let's look at the limit as x approaches 0 on the left. So x approaches 0 on the left. So these are for values of 0 less than 0. So use the equation when x is less than 0. And if we did use this equation, our y value that we get back is 5. And so we also want to see what's happening to the limit as x is approaching 0 on the right. Of g of x. And so since it's coming in on the right of 0 would be this middle equation. And so if we did that, well, we have something, in this case, 0 squared minus 2. If we do 0 squared minus 2, we get back negative 2. And so I can see I have a jump in my graph here because my y values on the left, or as x approaches 0, my y value on the left goes to 5, whereas x approaches 0 on the right, my y value is going to negative 2. Limit as x approaches 0 of g of x does not exist. Okay, so we also have to see what's going on at 3, because this is another spot which are in values of our inequality. So we ought to look at limit as x approaches 3 on the left. So left, that would be numbers less than 3. So this would be equation 2 of g of x. So this would be, we're going to go in and plug in 3 wherever we see an x. And g of x for the second equation. So this is 3 squared minus 2. Well, 3 squared is 9. 9 minus 2 gives us 7. Look at the limit as x approaches 3 on the right of g of x. So these are saying values of x which are bigger than 3, and values of x bigger than 3 says to use equation 3. So there's no x here. Plugging in 3 wherever I don't see where there's no x would just give me back 7. And so as we're approaching 3 on the left, with that one equation, we're getting closer and closer to 7. And as we're approaching 3 on the right, we're also getting closer and closer to 7. And if we're coming into the same number, the limit exists, and it's that number. So limit as x approaches 3 of g of x is equal to 7. Okay, there was one last question, I believe, that was in that piece. So I'm kind of scroll over for a second and grab it or see what it said. Does a value k exist such that the following limit exists? I think that is not going to the same question. It looks like a great question, so maybe we should look at that. Okay, so does a value of k exist such that the following limit exists? So using my limit laws, I can just go in and plug in 2 wherever I see an x here. And so let's just do that. So we would have 3, you see an x, I'm going to put a parentheses, leave it blank for a second. We're going to square that, plus k. I see an x, so I'm going to put a parentheses there. I'm going to come back and put in 2 minus 2. All over, I see an x, so parentheses squared minus 3. I see an x, so another parentheses plus 2. So going in here and wherever we saw an x, where I left my parentheses, we're replacing that x with a 2. And so let's simplify this down. So this is equal to, well, 3 times 2 squared. Order of operations, exponents have to come first. So 2 squared is 4. And then this 4 times the 3, well, that's 12. Plus k times 2. I usually write my coefficient in front, so I'm just going to rewrite that as 2k minus 2. All over. So 2 squared in the denominator is 4. Minus 3 times 2, so minus 6, and then plus 2. So let's simplify this a little bit. So 12 minus 2, those constants, that is 10, plus 2k is all over 4 minus 6 plus 2. So 4 minus 6 is negative 2, and negative 2 plus that 2 there would give me 0. Can we find some value of k to make this limit exist? Well, a limit exists if we're approaching a value and it's getting closer and closer to the same value on the left and the right. So a couple of things can happen here. If you have a rational function, the values which set the denominator equals 0 are either going to be an asymptote or it's going to be an open circle. And so we saw that when we had a graph where, you know, it was going along and there was just an open circle and then it continued, that the limit did exist. But if we have an asymptote, it doesn't exist. And so maybe if we go back to this original problem and let's, well, actually, we don't even have to. So the value where your hole would happen are the values which set both the numerator and denominator equal to 0. Okay. So vertical asymptotes occur when the values set the denominator equals 0, but not also the numerator. And a hole exists on the graph if it sets both the numerator and denominator equals 0. So we want to see, or we want to make that value of k to make that numerator equals 0 also. So to make the graph have an open circle, where it isn't undefined, because it's going to be undefined on any values which set the denominator equal to 0. So to make the graph, to have an open circle where it is undefined, we want to find a k such that it makes the denominator or numerator equal 0. So technically then we want to know when is 10 plus 2k equal to 0. So solving a linear equation, isolate your variable on one side, get all the terms without the variable on the other side. We would subtract 10 on both sides of this equal sign. We would be left with then 2k is equal to negative 10. Divide both sides by 2 to get the k by itself. We have negative 10 divided by 2 is negative 5. And so if we choose k to be negative 5, then this would have an open circle of the graph. And then let's go ahead and actually find that limit. So I'm going to extend the question. And so now find the limit. 1k equals -5. Oh, actually, sorry, that wouldn't make sense yet. Because I'd have to give you a value of a limit I wanted you to go to, and I'd have to look at this and actually factor and stuff. So let's not do part B. Okay. Okay, so we've been going for an hour now. So this would probably be a good time to take a little bit of a break. Any questions before we jump into a break? Okay. Okay, so let me pause the video and let's meet back here. Let's do 12 minutes, and 10 minutes is just a little too short, and 15 is just a little too long. So let's meet back here at 9:12, 9:13. Okay, so we just finished the section on limits, and we're going to jump into continuity. But I noticed this warm-up exercise, which is a good kind of try it, which covers things that we just learned from this last section. And so we're going to take about maybe 10 minutes to work on these, and then we'll come back together and I'll put you into probably breakout rooms where you guys can compare your answers. And then if you got stuck, then hopefully one of you in that breakout room could help. Best way of learning is kind of to teach it to somebody else and explain it. And then I will probably have this as a Canvas assignment that I'll have you guys upload your written work to this, to the Canvas assignment, and this is part of your participation grade. So I'm going to pause the video now for students to be able to work on it. Okay, so students had a time to work on this for a while, about 15 minutes, and then go in to groups for about 10 minutes and discuss it. And now we're just coming back together and we're just going to go through, because there's some problems on W3, W4, and W5. And so going through one of these, let's go through W3 together. And so we're looking at the limit as x approaches 3. So we could either go through this and graph it, or if we don't want to graph it, then what we can do when we're looking at the limit as x approaches 3, we have to look at what's going on the left-hand side of 3 and the right. So if we're looking at the left-hand side, this is when 3 is 0. I'm sorry, when x is less than 3. My computer kind of froze. So this is less than 3. And so we're going to use the first equation. Okay, so technically, since we're using the first equation there, instead of writing f of x, let's just write that first equation, x plus 3. And so now we can go in, and wherever we see an x, we're going to replace it with 3. So we see an x, then plus 3, and so we have 3 plus 3, which would give us a value of 6. We also have to see what's going on the right-hand side of 3. And so this is when our values of x are greater than 3. And so for that equation, there's 2 pieces where x is greater than 3, the second equation and the third equation. You want to use the equation that is closest to 3, which would mean that I'm using the second equation. And so let's just put in that second equation here for the limit instead of just f of x, which would be 2x minus 2. So we're going to go back in here, and wherever we see an x, we're going to replace it with 3. So we have 2, I see an x, so put 3 in there, minus 2. So this is equal to 6 minus 2, which is 4. So the limit is going to exist as x approaches 3 if the left-hand side and the right-hand side are the exact same number, which they're not. And so here we would say then the limit as x approaches 3 of f of x does not exist. So you're going to want to do the same thing for 4. This time you're going to look at 5. And so you have to look at the left-hand side of 5. So you would use the second equation. You would have to look on the right-hand side of 5 when x is greater than 5. That would mean you'd use the third equation. If those are the same values, then the limit exists. And the last one, let me just give you kind of a heads up on that too. That one, it says x is going to 6. Well, notice that 6 is not one of the n values of our inequality. And so x equals 6 would be just the fourth equation. And so when you're looking at that on the left and the right, you're still using that equation. And so then see if the limit exists there. I'll leave it like that. Okay, so we pretty much finished 3.1. You guys had some time, great, that you can look at and go over problems that we did similarly for this section. So I will create a assignment for this to turn it in to Canvas, and then it will be due by midnight tonight. If you get it in later, I probably won't knock points off if it's, you know, reasonable. So, and then only thing you have for homework then is the 3.1. And I talked to you guys at the beginning class. It sounded like a lot of you guys had started and just had a little bit left to go. So it was wonderful. Any questions? I'm going to stop the video and then I can take any questions.
Professor?
Yes.